Oh, good morning, everyone, and nice to see you all. And it's my pleasure to give this presentation in this webinars. And also thank you, Andrew, for the introductions. And to begin with, I would like to introduce what IZON is doing. And IZON was founded around 20 years ago. Actually, this month is our birthday, 20 years birthday. So IZON Science support the academic researchers and the industry scientists who are working with the nano-size biological particles by designing and manufacturing solutions for particle isolation and the physical characterization. So to achieve this, we have two main product lines. So the first is our nanoparticles analyzer based on tunable resistant pore sensing technology, TRPS. The other one is our size exclusion column for extracellular vesicle isolation, the QEV columns range. And in recent years, the QEV isolation platform has rapidly become a very popular method for the extracellular vesicle isolations. So that's mainly in the biomarkers development, EV research, therapeutic applications. Nowadays, we see increasing number of the industry inquiries to set up the larger scale UV purification. This is why we have this webinar today to show our solution from small to large. In which I would like to talking about the general UV isolation method. So we know that this list of 6 methods are generally used. For example, the first one, the differentiated centrifugation. So that is very old gold standard. So the previous researchers always using this one, and lots of people today still using this kind of method. So this one is by spin down the UVs by the centrifuge force. So different level of centrifuge force, you can palette the different levels of particles. So for example, for some low centrifuge speed to palette some like cell fragment or other things, and then very high centrifuge force like a palette like the small UVs. But this kind of method have some drawbacks we'll talk about later. Basically, it's like the high centrifugation force will damage the UVs, and it takes very long time. The second one, the density gradient centrifugations, which use gradient solution like the sucrose gradient to and under the centrifugation force, and then the UV will be purified under certain layer with the certain densities. This kind of method is comparatively clean, can get you quite a pure UV, but the thing is like also takes a long time. As you see in the image, it takes around like 16 to 19 hours. Also, some of the key components of the gradient, for example, the sucrose, will interfere the further experiments. And the third, number 3 is the size exclusion column, which we will pay more attention today. So size exclusion chromatography, they use the different bits, size of bits. And the UVs of larger size will elute first, and then particles with small size will elute later. By using these mechanisms, we separate the UVs by size. And for the fourth one, the ultrafiltrations. Ultrafiltration, they mainly use the molecular weight here, cut off like a membrane. The membrane can be different size. They usually used for the UV isolation is like 100 kilodalton and 300 kilodalton membranes. And then molecules smaller than this membrane hole size will passing through the holes, and then molecules which larger than this molecular membrane hole size will retain in this one. And currently, usually there are two variations of this like ultrafiltration. One is at the end. You can see it's like for example, the blue one is, let's say it's the UV stuff. It will go concentrate through here, but the drawback of it is, as you said, the blue things is accumulated in the membrane, which will largely affect these efficiencies. And later there's a tangible flow filtration. You can see the flow direction is different to the membrane directions. By this continuous flow, it will remove the UVs from the and large particles which is set on the membranes, so which increasing the efficiency of such like a filtration. So but this kind of method is usually considered as the concentrating method. It's not a kind of purification. We will talk about it later, because the myself guideline, the recent one mentioned that it's just a kind of like a concentrating method, not like actual isolation. It should be used like together with other method. For example, used together with size exclusion column to get like a pure EVs. And there's also method of immunocapture. This is based on the different antigens which the EV surface have. For example, the CD63, CD81, by using the antibodies which harvest those EVs with those markers. But this kind of method is can get you quite a pure EV, but you can see that it still takes a long time. But the drawback of it, you can see that it only captures certain EVs with certain antigens. It's not capturing the whole range of EVs, just the drawback. And also there's a precipitation method. Precipitation method uses some like agent to put into the solution to make the potential of the EVs drop, and then it's become like a pellet. Kind of method can be shorter or long, but the drawback of it is not that pure method, because all other proteins and other things will co-pellet with it. As you see in the bottom right image, so you can see that the SEC method is quite ideal. It's like with good recovery and specificities. You can see the precipitation method, the recovery is good, but the specificity is not good, which means it's not that pure. And recent years, there's more method apart from these 6 mentioned. For example, there's like a microfluid device, and then also like someone used the ion exchange columns for. But also the methods need to like use with other techniques to get a pure EV. And so let's focus more details on the size exclusion chromatography. How it works. Because like as you see here, so the size exclusion reasons have like a lot of holes in it. So when the sample passing through the resins, you can see that the small molecules will be trapped in those resins, which means they elute very late. And those large particles, one, for example, is EVs, they will not trapped by these holes, will elute fast. So you can see that by using these ways, we harvest the EV fraction and the proton fractions. So the two different like regions, we can harvest different proportion of those particles. And to mention why we shouldn't continue the UC method, because it has lots of drawbacks. First, it has very low recoveries and then time consuming. As shown in the left image, you see each step takes a long time. So it takes more steps and a long time to finish. And also by the right side articles, you see here. So after each, use UC method to isolate the EV, and it's done 4 rounds of the UC method use. And each round also takes the supernatant and can still find a lot of the EV markers on it. So efficiency recovery is only maybe around 5 to 15%. That means like each time, if you it also cost a lot of time, and then each time result in the low recoveries. And the second drawback is lead to the aggregation by the high centrifugation force. As this paper mentioned, by the electron microscope image, you can see that the EV aggregated together is quite often to happen, or under such a high centrifugation force, the EV just break. So if the UV you harvest is aggregated together, so it's lost its functions, or it's just the membrane breaks, it's also lost its function. That is not what we want. So the drawback is cannot efficiently remove the lipoproteins, as this paper mentioned. You can see that there's still high level of like ApoA1 here, and then serum proteins here. You can see quite a thick band here. And what's the advantage by size exclusion method? Basically, size exclusion method is a very gentle method because, like for example, our QEV columns only use can use like a PBS or sodium chloride as the buffers, which the UV will maintain its bioactivity in such solutions. Also, you see here, by the use SEC method, it will remove most of the carotene in the samples, while the UC method, you can see it here, so it's still quite high levels. And then, like this paper found, so by the SEC method, so it removed most of the contaminant proteins. You can see on the mass spec data, it's only have only a little by the SEC method, but there's still a lot by the UC method. So those papers conclude that the SEC was able to achieve high EV purities compared with the UC method. And also on the right side, this paper scores each different method. You can see that the SEC method give is very high scores. And as to the purity, resolution, recovery, score all give them like 3 scores, which is highest, and then also easy of use, comparatively easy to use. Take our column, for example, if our like 0.2 ml loading columns is only take like 10 minutes to run after you add in your samples. So which means the harvest from the time you add your samples and then harvest the purified UV fraction is only cost only 5 to 10 minutes for the 0.2 ml loading columns. And also this paper showing that the size exclusion columns will keep the UV activities. This paper compared the activity of enzymes after the UC method and then also the size exclusion method. You can see that here, but with the same amount of protein, protein levels. So you can see the after the SEC method got the higher purity, higher activities, and also if got the same amount of number of particles, or still like SEC method got the high level of activities compared with the UC method. So to conclude, like the SEC method, so it's suggested as quite easy to use, and then can keep its activities, and then also the time-saving method. And so we know that the International Society of Extracellular Vesicle published the MySafe guideline every several years. So this is the recent guideline of it. So by the SEC method, they suggest to report, like for example, the measurement and flow size and such, and also void volume of this. All these of our columns is deposited here, so it's easy to find all the information and then put it into the manuscript when you want to publish papers. And also to mention small things here, you see here it mentioned like the membrane-based method, like for example, the filtration is just considered as the concentrating method. So it's not that purification method. So you need to use for example, you can use the TFF as the concentrating step, and then but you still need to use other methods for the purifications, as it mentioned. Here, I'd like to show what our standard approach for the R&D side for the academic. So this is our solution for academic researchers. Our column can deal with different type of biological fluids, for example, plasma, cell culture medium, urine, or tears. So by using our columns and together with our automatic fraction collector, you can collect the EVs very quickly and and with high efficiency, and After that, you can use our systems for the particle measurement, and also using our like a concentration kit for the concentration, and then process to protein study or RNA studies. And as mentioned, yes, we have got a concentration kit. This kit is based on nanotrap particles. The particles have the bytes which have affinities to EV. So when harvest the purified EV from our QEV columns, if you still need a high concentration, so you can use such a concentration kit to harvest the UV and then with higher concentration. As you see that the efficiency is very high compared with the Amicon columns. You can see the Amicon columns by the RTQ PCR only got like around CT value around 35, but in comparison, so by using the nanotrap particles, the CT value is around it's less than 30, sometimes it's less than like 26. And so as solutions in the flowchart, so we provide a guideline to customers who need to follow in like adding different volume of the nanotrap particles following the QEV columns. But one thing need to be pay attention is affinity is not reversible, which means it will bound to the you cannot be removed from the UV. So that's why function study after the QEV concentration kit is the protein study or RNA study. For example, if you want to build RNA libraries after this, or if you want to send a sample to mass spec, so we suggest to use together with the QEV concentration kit to get a high concentration of the EV and process to those studies. And the current prepacked range of QEV columns currently is Gen 2 versions. So this is our latest version of the QEV columns have this range from the 0.15 mil loading to 100 mil loading. And as you can see, there are like a 10 mil loading, 2 mil loading, 1 mil loading, 0.5 mil loadings to fit different needs. But that is not to say this is only the range we can provide. So we have other customized columns which can scalable to our QEV 2700. 2700 means the loading volume is 3 liters. That's like a kind of industry scale columns which we will introduce later. So our QEV column have 3 types of resin. So each column loading volume has 3 types of resin. You can see there is 20 nanometer resin, 35 nanometer resin, and 70 nanometer resin. So different type of resin is used for different purpose. So 20 nanometer resin is usually used for small EVs or like some virus studies. So we recommended using the 20 nanometer resins. For the general cell culture medium, we recommended like using the 35 nanometer resin because it have a isolation range from 35 to around 400 nanometers. You can see here it's just for the cell culture media extraction EVs, and the 70 nanometer resins is mainly for like plasma EV isolation, because like we know that the plasma EV has got a lot of like the lipoproteins, to which will affect the mass spec measurement. So by using this kind of type of resin, so columns, we can remove more of the lipoproteins, which will bring much cleaner fractions compared with the 2 columns. And you can see here, so 20 nanometer resins can have the highest yield, and 35 nanometer resin, the yield is in the middle. 17 nanometer resins is the lowest. That is because we can imagine, because like a different 6 nanometer means like the size of the holes of the resin. So you can see that the larger, if the hole become larger, so they will also remove some of the small EVs, because you see here 17 nanometer resins, it definitely will remove some of the around 30 to 50 nanometer particles. If you do not want to lose this kind of particles, so for example, you may consider 35 nanometer resin and 20 nanometer resins. And then you can see this is different in the opposite side. So the highest the highest yield, which lead well, the purity is the lowest. You can see the lowest is less than 2E9 particles per microgram protons. And for the 35 nanometer resin, the purity is in the middle, so around 4E9. And the 17 nanometer resin give you the highest purity, which is around 6E9. So actually, it depends on your need. So if you want to need, so 35 nanometer resins is mostly used because it's a balancing of the yields and also the purities. But it depends on your detailed applications. Usually for diagnosis studies, they use the 17 nanometer resin because they want to remove as much as the lipoprotein as possible. That you can see here. Our columns have high capacity of remove those ApoA1 and ApoB. So that's what I mentioned is surface marker of the lipoproteins. Even though you may be surprised by this figure, well, why this one is so large, but you see, if you see check the y-axis, so the purified version is only contains 0.003% of ApoA1. So you don't need to worry about this one compared with the 20 nanometer resin and 35 nanometer resin. Actually, all the three resin remove most of the ApoA1 from the samples. For the ApoB, you can see that for the 20 nanometer resin and the 35 nanometer resin, there's still around 6% of the ApoB in it. Why people doing diagnosis study using the 70 nanometer, you can see that it's only have around like 1% of the ApoB. So in the purified extracellular vesicle fractions. So basically, to conclude, so QUV columns, so they can get quite high purities, and then we also remove the most proportion of the lipoproteins. It's to mention that we also have these two versions of the columns. One is for academic grade. Second one is like a GMP grade. What GMP grade column is fitting the GMP manufacturer. So the GMP grade GMP ready QUVs have each one have its own certification of like microbial abundance and endotoxin levels, which is manufactured in a controlled environment meeting the ISO standards. And this one is the large column, which is the QUV 2700 as mentioned before. So you see that it's a 3 liter loading one, it's 2.7 liter loading. And this one is the QUV 100 with 100 ml loading. This one is our QUV 10 with 10 ml loading. So we also have different loading volume of the GMP level columns to fit your different purpose. And as mentioned, we have the automatic fraction collector, which can be used for QUV 10 and below. That is to say, using with QUV single with 0.15 ml loading, QUV original with 0.5 ml loading, QUV 1 ml loading, 2 ml loading, and QUV 10 ml loading. This one can only use up to QUV 10 with 10 ml loadings. With this kind of device, so it will automate the UV isolation procedures. So you think here is have a quite accurate, very high sensitivity scale here. So you just put your samples here and then following the instructions and then add buffers, it will automatically harvest the UVs into fraction tubes. And say that this one will eliminate like human errors, because like even though the QUV column can be used manually, so manual operator create a certain bias by using multiple like AFCs. It will eliminate such bias and make sure you're using the same collection protocols for all your experiments. So that is to say standardize all your experiments. And that is the academic use of our QUV columns. As to UV isolation scale up, what I want to mention here, there are mainly two fields. One is for small volume, but need to handle multiple samples, for example, 100 samples in a day. That is usually for the diagnosis companies. And the other is to scale up is for about large volume, for example, 100 liters, 1,000 liters. So we provide a solution for both directions. Let's first talk about the isolations for the diagnosis. We provide the solution of a robot systems. It's called QEV Dexter. The Dexter can handle in 12 QEV original, that is 0.5 mil loading columns, and the QEV1 or 1 mil column, or 24 QEV single, that is 0.2 mil loading columns. It can handle those multiple columns by itself, so automate all the procedure compared with the AFC. AFC, you still need to manually put in buffers by your hands, but for this automate like a robot system, it will run by itself. So as you see here, this is a German group which have the 11 AFC. This image only show 9. So they use it to deal with multiple patient samples. And then later the publish papers will show later. And then they will have scale up their clinical studies. So that's why they need the robot system, the QEV Dexter here, to help them to run the samples automated. Because if you using the AFC, they still need to manually operate the touch screen. So by using the robot, it will definitely save them more time. So for the robot, it can handle around 100 to 200 samples a day, but based on different requirements. And this is the paper they published. So like this year, you can see the Nature Medicine paper. It's about this marker identifications. They using the QEV original. You can see it's using the 17 nanometer resin because they need to remove more of the lipoproteins. So less lipoproteins and then more purity of the EVs is better for the EV diagnosis. They also use the AFC, multiple AFCs, and collected the fractions like 7 to 10 for finish the study. After finish this study, they start to use the robot system to automate all the procedure. As you see that this is how the system works. As you see that is a rack hold the 12 baby original columns, and first one is show you the system to using buffers, adding samples to the column. Second video showing that after the buffer volume, which means it's collected, robot will move the rack to the collection. So 12 will place and start to collect the purified volume. The right side is the interface of the Dexter system. As you see that it's all the procedure is set. You just need to set in your laptop and then advise the device which sample need to collect, and then it will do it by itself. The image shows that you can see that the green one means that it's finished 10 sample now is working on the last 2 sample, and you can see all the information is recorded down here. You can see it's currently is continuing with the 11 samples here, and then it at a step of transforming 500 microliter of sample to column 11 here. You can see just pipetting arm will take these samples here and then put it into this well, and then put later after the buffer volume is collected, will pump in buffer through this this robot arm, and then adding the required amount of buffer, and you load it into the it's like a collection plates. And also you see here, there is a liquid sensor here. By using it, it will sensing how much liquid is still in the columns. So we should using this way to guide like when to add the buffer and to start to elute the column. So basically by using this one, there's no need to manually operate, and then it will all automate the EV isolation procedure, which is very helpful to if you are looking into running hundreds of samples a day, and for your project, this is quite ideal like a system for the setup to automate the EV isolations. And let's turn to the large volume side. We also provide a solution for the large volume UV isolation. it's either like the pilot run or pilot run. So for the principle is the same. We will show you later. Basically, when you have the different biofluids, for example, plasma, cell culture medium, for example, several liter of plasma, several liter of cell culture medium, because like the plasma can be directly after remove the cell fragment, the plasma can be directly processed by our like chromatography systems, which is our large columns. But for cell culture medium, due to the EV concentration in the raw cell culture medium is quite low, so we need to use the TFF system to concentrating it. So concentrating, for example, usually like 20 to 40 times is fine. So after concentrating, so also process to the chromatography and then purify the EVs with our columns. And later we using our TRPS technology which is like our single particle resolutions techniques to QC the particles. And after QC, it will be used for downstream studies. And for pre-pellet run, which was like 0.1 mil to 50 mil, so combination of our QEV TFF and QEV Zenko, and the same fit in the purpose, which make it a good solution for this kind of scale. And usually use the QEV 10 and the QEV 100 columns, and then sometimes using the QEV 250 mil loading. So if we consider it's a cell culture medium concentrating like 20 times, so you can see it's almost around like around in the range like 20 liters of the initial like cell culture mediums. And here is some like result of it. So each of our columns have default like avoid volume, which means like it not contain any UV particles. And then this is the UV zone we recommended to harvest. And after that is because we know that the resin, you remember the resin have small holes, and then protein will trap in that small holes, and then proteins will elute later. You can see that proteins start to increase in this region. So this is the ideal elution profile. So we harvest the UV here, and then the later protein region is here. Sometimes people need to harvest the part of the protein regions as a control during their like experiment. And the right images show us that why there is a need for the TFF concentrating of the samples. This is a cell culture medium sample, because you see that if you pre-TFF and then passing directly through the QEV columns, so you still can purify your sample, but you see the yield is very low, so indicated by the UV absorbance. But after concentrating 10 times with the TFF systems, you see there's a yield is very comparatively high compared with the one. So basically, if you want to get a high concentration of purified UVs from your cell culture medium, so it's like a recommended to use the TFF and to concentrate your sample first, and then pass in the size exclusion columns. And as to the yield, we can see here, this is detailed data. You can see that pre-TFF, if passing through the columns from these samples, is still around the E10, E11 levels. But when you using the TFF to concentrate the cell culture medium 10 times, you can see this yield is increased a lot. So you can see it's reached like the E12. Both resin can have similar results. Regarding the purities, so as I mentioned, previously mentioned, the TFF is just a concentrating method, because like you can see the purity is not that high. It's still like E8 particle per microgram proteins. This is the this is the initial purity. After the TFF is only, you can see the purity is remove part of the proteins. The purity increase a little, but not that much. So basically, any like a membrane-based molecular weight cutoff membrane-based those ultrafiltration method is only a concentrating method. It's not the actually give you a very pure EVs. But you see that in combination of the TFF and the QEV columns, you see the purity reach the E9. and this one also is reached to 3 E9s. So E9 is relatively pure of the EVs. And here is our TFF systems. We got it's a standard TFF systems, which got two scale to weigh the input and then permeate, and also got the console, the touch screens, and the pressure control valves. Now that is actually what it looks like. Here, this is what it is a hollow fiber with, usually we use 100 kilodalton and 300 kilodalton. For this one, the hollow fiber can help the together use with the TFF system to concentrating the cell culture media. That is how it works. For example, sample, we put the cell culture media here, and then by the pump, it will pump into the TFF cartridge or the hollow fiber, and it will run here like this. It will in the TFF and it can go back to this one. And this one is the molecular weight cutoff membranes. Any protein and liquid less than the size will be go through the permeate. And then by running this circle like a time and times, and then the permeate scale and the liquid here will be increased, so the volume here will decrease. So by this ways, the volume of the cell culture media is reduced and then reach the aim of concentrating, and the permeate will become larger and larger, and then the liquid and then molecular weight and the proteins with the molecular weight less than the membrane cutoff will be all in here by using such way. So it's concentrating the cell culture mediums. And next we need to mention, first we use the TFF to concentrating the sample, then we need to use the chromatography system together with the QEV to purify the samples. These automated chromatography systems have 8 inlet and outlet here, and it have UV sensors. The multiple inlet and outlet means you can run multiple samples, and the UV sensor is used to detect the EV peak. It's because the UV is usually set at 280 to detect the absorbance of the proteins in the EVs, and then because the EV is the first peak, it will detect the first peak, and then later the protein peak. And it also got a pH sensor, conductive sensor to monitor the cleaning of the columns. Because the size, our QEV size exclusion columns can be reusable. So just following our cleaning guidelines, it can reuse multiple times. And then by using the pH sensor and the conductivity sensors, it can guide the clean procedure of it. And this one also get the air sensor in it because to detect any air bubbles. If the air bubbles in the system, it will definitely damage the resin. When it happens, when the system detects the air bubble, it will stop, and then it will give you alarm to let you aware there's a lot of air bubbles in the systems. Usually there won't be. It's just it's a safety control of the air sensor. So here is a video of the introduction of our QEV access.
Welcome to the QEV Zinco, IZON's automated chromatography unit designed for scaling nanoparticle isolation. Compatible with our larger QEV Size Exclusion Chromatography columns, as well as our more industrial-sized customized columns, the QEV Zinco accommodates a wide range of sample volumes up to around 400 milliliters. Built with a compact design, the QEV Zinco packs a punch with its capabilities. Let's explore the components. With 8 inlets, you can add a variety of solutions into your workflow, including buffers, samples, and cleaning agents, for both the Zinco unit and the QEV column. The first valve controls which inlet draws liquid into the QEV Zinco, powered by an upstream pump. The liquid then flows through 2 key components, a pressure sensor and an air detector. The second valve then directs the flow through the QEV column in standard forward mode. Reverse mode is available for column cleaning, or you can bypass to skip the column. Post-column, the liquid passes through conductivity, UV, and pH sensors for analysis. At the third valve, you have 8 outlet options to control which volumes are collected or sent to waste. The QEV Zenco's flow path diagram helps ensure straightforward setup and operation, while live data monitoring covers flow rate, pressure, temperature, conductivity, UV and pH. When setting up your method, you have precise control over multiple parameters, which are accessible here. Priming, loading, collection and cleaning processes can be configured at this stage too. You can also save and import method setups for future runs, saving valuable time. Let's follow a run through a QEV 100 70nm column. The QEV Zenco will perform a series of draws with appropriate inlets automatically switching after your predetermined volumes have been taken. You can monitor parameters in real time and display up to 2 graphs simultaneously. Here, you can see the range of parameters that can be selected. In this case, we are choosing to display UV and pH over time, as well as conductivity and temperature. We are now at the point where we have already primed the column, and we're now eluting the sample. You can see the UV reading rise, indicating the start of the peak in particles. You can use this UV trace to check that your sample is eluting as expected, and to identify any issues early on. In this case, we are isolating extracellular vesicles from plasma, and we have entered our desired purified collection volume in the method setup based on our analysis of previous elution profiles. The outlet will change from our collection vessel to waste based off what we established in the method development phase. You will notice there is a dramatic increase in the UV reading, indicating the proteins separated from the sample. The QEV Zenco has now switched to cleaning mode, starting with buffer. Sodium hydroxide then flows through the unit, causing a dramatic pH shift. Once the cleaning solution is flushed out, the pH returns to physiological levels, preparing the tubing and column for the next round without residual contamination. Streamline and scale up your nanoparticle isolation process with the QEV Zenco, designed to deliver precise, efficient, and high-throughput isolation for your lab.
As you see in the video, so it's all around in the QEV column for the EV isolation automatically. And as you see that there's 8 inlet ins, which means like you can put like multiple samples in the other outlet, and then after running one sample, and the system can clean the columns, and then you can run another sample. So you can see run multiple, what I mentioned is run multiple sample automatically. So that is a great like improvement compared with using the AFC or manual run the systems. And here is a example run of the plasma. So you can see here the system have guided the collection of the first peak, because like we know that the plasma is quite a complex. It's a very high, rich in protein. That's why you see the protein peak is very, very high. First small peak is the EV. So the system collects the EV and then start to elute for the protein things, because like usually we don't need to use the protein things. We just let it go into the waste. But for the EV, you can see there's 2 points. The system can be automatically detected by the UV rise and collect its fractions. And as mentioned in the video, so the Zenco system can be used for up to 400 ml loading to UV columns. 400 ml loading, if we take the TFF concentrating into consideration, for example, if 20 times and 40 times concentrating, that means that the QEV Zenco can be used to handle from 8 liters to around 16 liters, so 8 to 16. So that's like a QEV Zenco handling small, under 20 liters of the cell culture medium. And for even large volume of cell culture medium, for example, more than like, for example, but I need to mention that is for a run. Usually you can use the column for multiple runs. That means you can increase its ability to handle more cell culture medium, as I said, like using the different inlet for example, run the sample twice. So you can see if you run the sample twice, you can increase it to around 16 to 32 liters of cell culture mediums, which it can handle. As to the pilot run scale, so we usually have we call it a QEV pure path. So as you see, the purpose it is a total solution will provide to the industry customer by these diagrams. As you see for the purple part, so usually like cell culture media need to do a first step is the clarifications. It is by different theories of different size of the membrane. You can see here is, for example, it's a 30 micrometer, 10 and 5 micrometer for this membrane to fill out of the cell culture cell fragment. And then we using the this one is large industry scale TFF systems to concentrating the samples. And also for the isolation part, we use our largest chromatography system called the QV Big Zenko to handling the large columns with the QV 2700. And then later we use the Extracellular for the QC part. And then if customer have a downstream requirement, for example, there are some like bioactivities and for the QC, and then it can also be done to form the total solution here. As you see in the image, this is a large industry scale TFF system, also the large like a QEV 2700 column, which can handle in around 3 liters of the cell culture medium. You can see the purple, the red color here is currently running concentrated samples here. And this diagram shows how it works. For example, the cell culture medium, if it is quite if the raw cell culture medium is quite complex, you need to be dilute and then form the dilute cell culture medium, and then passing through a series of the clarification filter, for example, 17, 50, 30, 10 micron. And then after filter those like cell fragment out, and then we can start to process with the TFF to concentrating the samples. After concentrating samples, sometimes if the concentrating is too much, or after concentrating if the sample is too whiskey, and it need a further dilute with buffers to load before loading the column, because like the column have a loading capacity, because like if the protein is more than 17 microgram per ml, so it may affect the flows of the column. So for this example, you need to dilute the samples a little and then passing through the chromatographies and then to get the pure EVs. As you see in the left image, so the raw condition median, the purity is quite low. And after the Size Exclusion columns, and it will reach quite a high purity, reach the E9 level. So it's very pure, quite a pure EV now. So to finish, like let's introduce the big Zenko device. You can see it's an industry scale device, because like you can see it has the diaphragm pumps feeding the large column, and it has very high flow rate, and also it has all the sensor required. System also meeting the GMP standard, so it's fitting the GMP like a manufacturer. And as you see, it's like a stainless like a surface. It's easy for cleaning. And this is some more image of the large columns, and then the big Zenko device you can see here is this one is used for large volume process. This device can be used for like more than 1,000 or 2,000 liters project, because using these columns multiple times, it can handle in such like large volumes of the culture medium. It's an example of the pilot runs, because with the UV sensor guide, you can see that the column can be reused multiple times. But the detailed reuse times depends on different sample type. For this customer sample, you can see the columns reused 30 times, it still maintain its efficiencies. You can still get quite a few of the EVs and some protein concentrations here. If you divide this by this, we can see the purity is above 2E9 or above 2E9 purities. And you see when it's at like 20 rounds, 30 rounds, so the proteins separation efficiency start to decrease, but for the EV peak, it's still good. Then we still suggest like to do like so in that case, like the column of industry scale can be used like multiple times, at least like 10 or 20 times reusable, and then which saves the cost. And last, I would like to have a very short mention of our EV characterization. device. So our device is based on TRPS technology. So here is the principle of a
Tunable resistive pulse sensing, or TRPS, is a technique that measures particle size, charge, and concentration. TRPS measures particles from 50 nanometers to 20 microns as they pass through a tunable nanopore. When particles cross the pore, they block the flow of current, resulting in a blockade signal. Each signal corresponds to a single particle passing through the pore. Each signal can be analyzed to extract detailed information of the thousands of particles in the sample. The height of the signal determines the size of the particle. The duration or time taken for a particle to pass through the pore allows determination of particle charge. The rate at which particles pass through the pore determines the sample concentration. TRPS enables individual measurement of particles in a sample. The high level of detail provides confidence in your experimental results and enables you to get representative information on your sample.
As mentioned, this device, it can measure like a 50 nanometer to 11 micron. So it's measure particles. It's measure each particle passing through the nanopore. So it's actually a single particle resolutions. It's not like any optical method that give you like a estimated number. So papers like this paper shows that going in compare with the TRPS, so TRPS can identify the actual formal samples, but other techniques such as light scattering method, NTA, and also NetFCM, all missing some of the peak. So which means like the proof the TRPS